Okay, welcome back. So in this video, we'll see a couple of examples for computing partial derivatives. So let's start with a simple idea. We just take a vector and we'll define a function f by taking the scalar product of this vector and the input vector. So that's a function on r to the n that maps to real values. For a vector a equals a1 to an in r to the n, define a function f mapping r to the n to r by saying f of x is defined as a transpose x, or in other words, the sum of the ai times xi, I from 1 to n. Okay, what about the partial derivatives of that function here? What can we say about those? Well, first, fix some point x star. We always want the partial derivatives at a point x star. And some j, some direction, some axis in 1 to n. Then this one-dimensional function g, t of lambda, that just looks like f of x star plus lambda ej. So basically what we get is all the x's are now x stars, and xj is replaced by x star j plus lambda. So we still have the sum from 1 to n, with the exception of the index j. So all that stays the same. But we now have to add a j x star plus lambda star j, of course. Okay, so this summand here actually changes. And that means what we get is basically a transpose x star plus aj times lambda. So that's the only part that is dependent on lambda actually. And well, what that means for the derivative is pretty clear. G prime of lambda is then aj. And in particular, g prime at 0 is also aj. Okay, and that means the partial derivative df dxj at x star is just the constant aj, no matter what x star we chose. And if you compute all these partial derivatives, then the gradient of f at x star will simply be a1 to an, or just the vector a. Okay, so that function has a very simple gradient. How about the Hessian? Now that can also be computed easily because d squared dxi dxj of f at a point x star, well, that's d dxi of aj, and aj is a constant, so the derivative of aj will just be 0. And that's true for every ij combination, no matter what. So the Hessian of f function is the all zeros matrix. Okay, so that's a simple analogy to the one-dimensional case. You remember that for functions in 1D, if you have an f of x defined as some constant alpha times x, then you remember the derivative is alpha. So in this case, the same thing happens. The gradient is now a, and a is basically the same thing as a constant alpha here. Yeah, just a vector form, constant. So let's go a little step further. Let's consider a quadratic function. So let f r to the n to r be defined as f of x equals x transposed a x for some matrix A. In n to the n. In r n times n. Okay, and again the question is, what are the partial derivatives of that function? What is the Hessian of that function? And how can we find that out? First thing we'd like to do is write that function in explicit form. So what is this f of x actually? F of x1 to xn. How can we compute that? Well, we have x transposed. Then we have this matrix A with components alpha 1, 1 to alpha 1n, or in the first column we go to alpha n1 and then to alpha nn in the last entry here. So that's how this matrix looks like. And we multiply it with a vector x1 to xn first. So if we do this, this left-hand side vector, I just copy that one and write it in explicit form, x1 to xn. Now what happens here? Basically, what we do is we multiply each row of that matrix A by the vector x1 to xn. So in the first row, we get alpha 1, 1 x1 plus alpha 1, 2 x2 plus alpha 1, 3 x3 and so on. So what happens here is we get the sum of the alpha 1 I x I from 1 to n. And that's true for all the rows, only the row number changes. So that goes up to alpha ni xi I from 1 to n. And now if we just multiply those two vectors, so we take a scalar product here, and this is x1 times the first sum plus x2 times the second sum, and so on up to xn times that last sum here. And what you can see, if you look a little closer, is that is the same thing as the sum I from 1 to n, and then j from 1 to n, alpha ij xi xj. Okay, so basically we just multiply all the combinations, and for xi times xj, the coefficient is exactly alpha ij. So with this form, we should be able to compute the derivatives. So what about df dxk? The kth direction. Well, basically everything that does not contain an xk vanishes right away. So We'll only keep entries that have an xk in them. And if they only have one xk in them, then what do we get from those? Well, we get an alpha x, or alpha I k, sorry, x I. Only exception, I should not be k, otherwise we would have an xk squared, and that is different. So that's where the k appears in the second variable. So that second variable vanishes, the first one stays. Of course, it could also appear as the first variable, so some term of the form xk times xj. Then just the second one would stay, but we'd have a coefficient alpha k j xj, j from 1 to n. And again, we need to exclude the case that j equals k. So this special case here, both indices are k, so we have an expression of the form alpha k times xk squared. If we differentiate that, we get 2 alpha kk xk. Okay? So that's what the derivative looks like. And what we can do now is we can take these two here and distribute them into those sums. Yeah, you will notice these are missing the kth coefficient, and we can just take one of these into every sum. That makes it a little easier to write. So we have the first sum, alpha ik xi, and then the second sum, j to n alpha kj xj. And we don't need to exclude the kth summed anymore if we just distribute that evenly. Okay. One special case, if A is symmetric, this looks even nicer. But let's first write this in matrix vector form once more. If we do this in matrix vector form, then this becomes X transposed A EK plus EK transposed AX. And just as a remark, if A is symmetric, these two are the same, and this becomes df dxk at x is 2 ek transposed ax. So again, there's a similarity to the one-dimensional case. So this time the Hessian is a little more interesting, actually. So let's try that one. Further. If we differentiate once more, so take that derivative by dxk and then differentiate that by dxl. Again, have a look at this here. So this is how it looks after one differentiation step. Now we differentiate that by dxl. What remains is only the coefficients where we either have xl here or xl here. So alpha lk and alpha kl will remain. So this is alpha lk plus alpha kl. And again, if A is symmetric, then those entries are the same. So what we get then is 2 alpha kl. Okay, so in other words, again, if A is symmetric, then the Hessian of A, the Hessian of the function f, is just 2 times the matrix A. And again, something that should look familiar from the one-dimensional case. If you differentiate a quadratic function, then you get 2 times x instead of x squared. Yeah, basically the same thing happens here. Finally, one more concrete example with actual numbers and actual dimensions. Let's consider the function defined on R2, maps into R. Defined as f of x1, x2 equals x1 e to the x2 plus 1, like this here. And we want to compute the gradient and the Hessian of that. So first, d dx1 of f of x. So what we do is basically we fix all the x2 entries, we treat those as constants, and we differentiate the function as if it was just dependent on x1. So what we get then is just e of x2. That is a constant in our viewpoint now, and this plus 1 vanishes. Okay. If we do the same thing with respect to x2, now we treat the x1 as a constant. We just differentiate with respect to x2. What happens is x1 e to the x2, and the plus 1 again vanishes. Okay, so the gradient of f at x is e to the x2, x1 e to the x2, or e to the x2, 1, x1. Now if we were to compute the Hessian, we need to compute 4 partial derivatives based on these two. So let's start with the first vector here. So this e to the x2. Let's differentiate that further. So that's d squared dx1 squared of f of x. If we take this e to the x2 and differentiate it once more with respect to x1, then we just get 0. If we differentiate it once more with respect to x2, so d dx2 of e to the x2, then we get e to the x2 this time. And we'll do the same thing for the second coordinate now. So let's compute d squared dx1 dx2. So that means we need to differentiate the expression x1 ex2 by x1. So this expression we're taking now, and we differentiate it by x1. What we get is e to the x2 again. And finally, d squared dx2 squared f of x. So basically we take in this expression x1 e to the x2 and we differentiate it with respect to x2 once more. So this again yields x1 e to the x2. And now taking all of these together, we get the Hessian. So HF is now first entry here. That was 0. So this is the entry in position 1, 1. This is the entry in position 2, 2. So we have a 0 here. We have an x1 e to the x2 here. And these other two entries here, those are in positions 1, 2, and 2, 1. E to the x2, e to the x2. Okay? And one thing that you should observe is these two entries here, those are equal. So in this case, it did not matter whether we took the derivative with respect to x1 first and then once more with respect to x2, or the other way around. And the question is that true in general, or when will this be true? And we learn a little more about this in later sections. Okay, that concludes the examples about partial derivatives. As usual, there are a lot more examples on the exercise sheets, so you can work through these to get some more practice with partial derivatives. Next, we'll extend the concept a little to directional derivatives, and then finally generalize the idea of taking derivatives altogether and see that we can get a concept that we can actually work on in multivariate settings.